Problem C. Dog cannot catch. In this presentation, we will define our approach to the problem, explain our assumptions, create and analyze our mathematical model, and explore the model's limitations and how it can be improved in the future. To approach this problem, we first made an ODE model of Fritz's jaw movement and tracked Fritz's mouth in the video to corroborate the model and determine what constants make the model behave the most realistically. Then, we modeled errors in head orientation and distance prediction using gravitational kinematics and determined how these would affect catching ability. Finally, we estimated the effect of the initial throw, object size, and air resistance. There are three main factors that cause Fritz to fail the catch. The first two stem from Fritz losing line of sight to the food when his mouth is open, requiring him to calculate the parabolic trajectory from that point on in his head. This leads to potential errors in positional prediction as well as errors in mouth timing. The third main type of error stems from elongated shapes, where a successful catch requires rotational prediction and a twisting of the head by the right angle.
We need to make the following assumptions. The mouth is circular and the objects are spherical. The dog moves to the correct left-right position and longitudinal orientation before the catch. During the catching phase, the body is stationary. The dog only tracks motion with its eyes, and the eyes are able to accurately track the position and velocity of the object. The dog loses sight of the food once it opens its mouth, and the dog has a good sense of its own mouth mechanics. The dog only makes one catching attempt. For the mouth to successfully catch the object radius, denoted by big R, must be less than the effective mouth radius, which is composed of the following three parts. The radius of the mouth, R of t, multiplied by the orientation angle error, cosine of theta, and subtract the positional offset, delta x.
Let the y position of the dog's cheek be 0, and the x position of the throwing hand be 0. Therefore, we can let the initial position be 0, y0, and the initial velocity be x prime 0, y prime 0. Finally, let the mouth radius be half the distance from the nose to the chin. We estimated that the nose is 6.5 centimeters above the cheek. Let the time be 0 when the object is first thrown. As shown in the diagram, there are three critical times for the catch. When the dog starts opening the mouth, defined as TA, when the object reaches the mouth opening, defined as TB, and when the object reaches the cheek, TC. We want to find the effective mouth radius at time TB when the object passes through the mouth opening.
To model the dog's mouth, we interpreted the jaw as a moment arm and the jaw muscles as a source of torque and assumed the system to be a damped-driven harmonic oscillator. Such a system can be described by an ODE using moment of inertia I, friction constant C, and a spring constant K to relate the various derivatives of angle. This torque-based ODE, describing the jaw as a hinge, can then be converted to a force-based ODE by dividing by the length of the moment arm. To solve this ODE, we first use e to the st substitution to find the homogeneous solution. We also assumed that the system is overdamped, as the dog's mouth does not exhibit small oscillations. For a constant driving force, the particular solution is given by f over k, and the total solution is the sum of both solutions. However, f cannot be a constant driving force as the mouth opens and then closes. We assumed f of t to be a square bump and solve the ODE for opening force F1 and closing force F2. If the applied force switches from F1 to F2 at time t, the position and velocity of the first solution at time t can be used as the initial conditions for the second solution. This yields a piecewise function r of t that is continuous and differentiable. Now, we need to find values for the various constants in the model that match how Fritz's mouth actually behaves.
Here we have two clips. One of them is Fritz trying to catch a taco and the other one is Fritz trying to catch a burrito. If you watch the compilation video by Fritz Dog, you'll probably find these clips in the video. However, in these clips, we noticed that there are boxes and colorful points following Fritz. We created these annotations by training Ultralytics Yellow V8 on the Stanford Dog dataset. The Stanford Dog dataset is a compilation of many dogs with point annotations for specific parts of the dog, like the legs, paws, ears, but more importantly for us, the chin and their noses. We choose to take a clip with a smaller food object, so it won't obstruct as many points that we would need. In this clip, the dog is attempting to eat what appears to be a meatball. A few recorded points were inaccurately positioned, although the majority were correctly positioned. To address this issue, we manually identified and fixed these points. After averaging a list of points together and doing the necessary conversions like removing the distance between the chin and the bottom of the mouth, we were able to obtain this graph. The red data points correspond to the instance when Fritz started opening its mouth and finished. Note the dip and rise after the red data points. This can be attributed to a last-ditch effort by Fritz to seize the meatball by slightly closing his mouth and opening it again.
Fritz wants the mouth to close when the object reaches its cheek. Otherwise, the object may cause choking or bounce out of the mouth. The mouth opens at TA and closes at TC. This time interval T-chomp is about 0.45 seconds. The difference between TB and TC is the time for the object to go through the mouth, which is approximately the mouth length over the falling speed, assuming the speed TB and TC are close. From the graph, we can already see a problem. The mouth can't open wide enough at TB for a fast-falling object. In fact, the mouth almost closes. When Fritz opens his mouth, line of sight to the object is blocked, so he tends to assume the object continues in a straight line. The dog determines TA based on the tangent line approximation of the current position and velocity, which can be derived from the equation below. Before opening the mouth, Fritz can adjust for error by realigning. Once the mouth opens, however, line of sight is lost, so observational errors can no longer be adjusted for using visual feedback. This leads to a positional and timing error, which cannot be easily corrected. We add subscript 1 to denote Fritz's perceived time, and 2 for the actual time. Here are the calculation of the time and velocity at the time when the dog thinks the object reaches its cheek, and when it actually reaches its cheek. We ignore air resistance for now, assuming the x velocity stays constant. Then the x position error due to parabola misestimation equals to the product of x speed, the time difference between the reality and approximation, and the sine of the trajectory's latitudinal angle.
Now, we will quantify how the dog's misestimation of latitudinal head orientation affects catching outcome. The projection of the mouth width r onto the normal of the trajectory gives the width the food has to pass through to be caught. This width is given by r times cosine of delta theta. Orientation error is also affected by the tangent line approximation the dog makes for the parabola. The food's path will curve downward in the period when the dog can't see the food, leading to an additional error. The adjustment for this is not significant, however, until delta theta becomes very large. Even if the dog is 20 degrees off, the effective mouth width is still 93% of what it would have been. Thus, the dog does not have to orient its head very precisely. We can now bundle the mouth and kinematics models together to calculate the size of the largest object the dog can catch in different conditions. Here, delta x is a function of the initial height and velocity components of the throw. Thus, the effect of different throw properties on catching success can be analyzed. For now, the food is assumed to be spherical and air resistance is assumed to be negligible, but these factors will be addressed later.
We first simulated the effect of different x and y initial velocities on maximum catching radius. A high x velocity makes catching harder due to greater positional error from the parabola miscalculation. A low y velocity also amplifies the positional error as the object takes longer to fall. A high y velocity also makes catching harder due to mechanical limits on how fast the mouth can open and close. Overall, there is an optimal range of y speed, while faster x speed generally makes it harder. The effect of initial height is similar to that of the initial y speed. In the graph below, we fix the initial throw angle to 45 degrees. If Fritz and his owner are at the same height, a higher throw is easier, but at much greater elevation differences, Fritz's mouth mechanics are the limiting factor. Predicting a parabolic trajectory is not a straightforward task, so it's understandable that Fritz struggles to learn. As he gains more experience, the error coefficient, AX, will decrease, so Fritz will be able to catch bigger objects. Let's look more closely at the relatively subtle initial y speed effect by keeping the x speed constant. When the y speed is low, the error mainly stems from the parabola misestimation, but Fritz can improve this through learning. When the y speed is high, however, mouth mechanics are the limiting factor, which is harder to improve by learning.
We used the quadratic drag equation to incorporate air resistance and simulated the results for 3 different objects. We found air resistance makes catching easier, which may seem counterintuitive, but it makes sense because when drag is high, the vertical speed is close to the terminal speed, which better matches the dog's linear approximation. The speed will slow down in x, but that's way less than the effect of gravity.
If the object is non-spherical, the dog has to predict the rotation of the food and twist its head to match its mouth with the nearest point. Additionally, long and rigid objects have to be caught by the center of mass. Deformable objects bounce less, however, so Fritz can catch those by an edge and hold on. So overall, the most important factors of the throw to Fritz's success are the throw speed, horizontal components of velocity, and the size of the object. On the other hand, the most important factor of Fritz's behavior is his ability to predict the food's parabolic trajectory in the terminal phase when Fritz cannot see the food he is catching. Although this model is quite complex, it does not account for everything. In the model, the dog has good enough control of its body to move its head to the correct position. It also correctly perceives the food's position and velocity up to the point where it breaks eye contact by opening the mouth. Furthermore, only spherical objects were considered, so we didn't model rotation in flight. Finally, if the food bumps into the lips, we assumed the catch was a miss. For floppy foods like steak, a collision with the top lip may not make the catch unsuccessful, however. To address these limitations, we could simulate the dog's body to calculate how precisely force input has to be controlled. We could also analyze factors such as velocity and positional misestimation that cause errors once the dog has learned parabola mechanics. We could also model the behavior of non-spherical objects with their moment of inertia matrix and account for non-rigid objects by loosening the catching condition. And finally, a more realistic potential function that remains low for low and intermediate width values and becomes high closer to the maximum width of the dog's jaw can be used.
Here are the references. Here are the next page of references. Lastly, we express our gratitude to Professor Landi, our coach, for providing moral support throughout the contest and training us in the weeks leading up to it. This concludes our presentation, and we appreciate your attention. Thank you.